Hi, my name is Ronen Shekel. I'm a PhD student in Johan Bromberg's lab in the Hebrew University, and I will talk to you today about the fundamental bounds of wavefront shaping of the spatially entangled photons. Classical wavefront shaping deals with light, such as a laser, propagating through some scattering medium, which results with this seemingly random interference pattern, which we call a speckle pattern. It has been shown already in 2007 that using some feedback loop from a camera and a spatial light modulator, or on a SLM, so the light can be shaped before propagating through the scattering medium such that constructive interference will occur at this desired spot and we'll get a nice focus. Now, in classical wavefront shaping, you might ask, does it matter whether we shape the light before the scattering or after the scattering? Well, it turns out that it doesn't matter. The enhancement eta, which we define as the ratio between the intensity in the desired spot after the optimization divided by that intensity before the optimization, scales linearly with n, the size of the system, and we assume we have n pixels in the SLM to shape these n modes, and has a linear prefactor of pi over 4, which we will get back to later. Now we want to use wavefront shaping for spatially entangled photons. So what do I mean by that? Well, the most popular source for entangled photons is SPDC, spontaneous parametric down conversion, where a strong pump beam hits some nonlinear crystal, and with some probability, one pump photon will be annihilated and two red photons will be generated. From momentum conservation, so if one of the photons goes at some angle theta upwards, so the other one will go at the same angle theta downwards. And this results with a highly entangled state. To measure this in the lab, we can place two single photon detectors in the far field. One of them is fixed and the other scans the transverse plane. And you measure coincidence events, which are events where both photons arrive at the detectors simultaneously. Performing these measurements, we get this highly localized correlations, where basically we get to these coincidence measurements only when both detectors are exactly on the opposite sides of the optical axis, or when the sum of the two angles is exactly 0. However, if now these entangled photons propagate through some scattering medium, so now we will get these strong quantum correlations will be scrambled, and you will get this so-called two-photon speckle, which is a speckle pattern in the correlations between the photons. Given one photon is here, the other one won't be exactly in the opposite place, but rather it will be smeared all over the plane. Our goal will be to use wavefront shaping tools to relocalize these correlations or to undo the scrambling. In the past decade, there have been several works doing just this, using wavefront shaping tools as is for shaping entangled photons. But in none of them did they consider whether this linear scaling with a prefactor of pi over 4 actually remains the case also when shaping entangled photons. In this work, I want to show that the two-photon case is actually much richer, and there are several new questions that arise, such as, now that you have two photons, so what should we do? Should we shape only one of the photons, or should we shape both of the photons? And does the relative position of the two detectors matter? Because in the classical case, we have only one camera. Now we have two detectors, so there's some relative position to think about. I will also show that having the SLM before or after the diffuser does matter in the quantum case, unlike the classical case. As a spoiler, I'll say that we will see that indeed there's some quantum configuration where we get the same classical scaling with a linear prefactor of the enhancement of a pi over 4. But in other configurations, you will see that sometimes you get reduced enhancement, sometimes you get improved enhancement, as we shall see soon. This is also a good time to say that we assume in this work that both photons propagate through a thick scattering medium, which we will now model as some random unitary matrix, and also that this is a theoretical and numerical study. Before we get to the actual configurations, it is very instructive to think of this system in the Klitschko advanced wave picture. The advanced wave picture considers exactly these sort of experiments, where entangled photons generated via SPDC propagate through some general linear optics setting, and we perform these correlation measurements, these coincidence measurements. And it proposes an analogous classical experiment where one of the detectors is replaced now by a laser, and the nonlinear crystal is replaced by a mirror. So light is emitted by these lasers, back propagates through this general optical system, is reflected by the mirror, and is finally the intensity is measured in this camera. And Klitschko's picture guarantees us that the intensity measured in this classical experiment will be the same as the correlation that we will measure in the quantum experiment. So let's move on to the actual different configurations. The first configuration we will consider is that of where we shape only one of the photons. So the SLM is placed after the beam splitter and after the scattering medium. Considering the advanced wave picture counterpart, so the laser propagates first through the SLM, is then scattered again, and is finally measured. So this actually seems very similar to the classical case. And indeed, we show numerically and analytically that the enhancement indeed is linear with n and has a prefactor of pi over 4. The second configuration we consider has the SLM shaping both photons after the crystal and before the scattering medium. This is probably the most popular scenario in these quantum wavefront shaping experiments. Considering this scenario in the advanced wave picture interpretation, so the laser actually first scatters, is then shaped by the SLM, which we for now assume that is imaged to the mirror plane or to the crystal plane, is then scattered again and is finally measured. So in this case, we show, again, analytically and numerically, that now the enhancement prefactor is pi over 4 squared, which is lower than pi over 4. So it is a reduced enhancement. Intuitively, why does this happen? Because in this scenario, the SLM is actually illuminated by a speckle pattern. So the SLM has a lower number of effective degrees of control. You can think of pixels that are illuminated with a dark speckle, so it doesn't matter which phase you put on a place where you have no electric field. However, despite this reduced enhancement in this configuration, there is a special symmetrical case. If both of the detectors are placed in the same location, where they're both at x equals 1 in their respective axes, so it turns out that we actually get perfect focusing. In the Klitschko interpretation, so that means that we send the laser and we don't try to focus to any arbitrary spot on the camera, but rather to focus back to the same spot that coincides with the location of the original laser. So this is somewhat surprising, and we explain this in the language of OPC, of optical phase conjugation. Optical phase conjugation is known for many decades already. It describes considers some image propagating through some aberrating or scattering medium, and it is reflected by a phase conjugating mirror, which is a mirror which performs phase conjugation to the electric field. And it turns out that from the symmetry of Maxwell's equations to time reversal, this image will return exactly to its original state. And indeed, the optimal phases to place on the SLM in this configuration are exactly the phase conjugation phases of the field coming in the advanced wave interpretation. Good. The third configuration that we will consider is having the SLM shaping both photons after the scattering medium. And I remind you that in the classical case, it was the same. It didn't matter whether SLM was before or after the scattering medium. Here, we consider again the advanced wave picture interpretation. So now light is shaped by an SLM, is then scattered and scattered again, and then hits again the same SLM. So this is actually very important because in regular wavefront shaping protocols, so the most naive optimization algorithm actually goes over the SLM pixels one by one, finds the best phase, and moves on to the next pixel because the different pixels are independent. However, it turns out in this configuration, so the phases that we will put on some of the pixels will affect the field that will hit the other pixels in the second time it hits the SLM. So this actually makes finding the optimal phases a self-consistent hard optimization problem, which while we don't show this rigorously, so we believe this to be an NP hard problem. However, for a finite size, we can still search for good phases. And numerical simulations show that we are able to get an enhancement which is actually better than the classical enhancement. You get a 0.89. We don't have some physical intuition to this number, but it's better than pi over 4. And what we can say is that even though this turns out to be a harder optimization problem, it is worth it because we get a better enhancement. Of course, this depends on the exact system parameters and yeah. So also in this third configuration, so there's again a special symmetric case where again where both detectors are in the same mode, and also here we show that we get perfect focusing. To explain this intuitively, so I hope I convinced you before in the second configuration that if the mirror will be translated into a phase conjugating mirror, so we'll achieve perfect focusing. But now the SLM isn't in the mirror plane, so what can we do? So now we notice that if the electric field in this plane has a flat phase, so a regular mirror acts as a phase conjugating mirror if the phase is flat. And in fact, the same thing is true also if the phases are of 0 pi, because minus 0 is 0 and minus pi is pi under 2 pi modulo. So basically, if the field is real in this plane, so the mirror will act as a phase conjugating mirror, and we will get perfect enhancement. Now, since, as I said, each mode can be with a phase of either 0 or pi, so there are actually 2 to the power of n such combinations, which will all result with perfect focusing. So it turns out it's pretty easy for the SLM to find the phases to apply, such that in the mirror or in the crystal plane, the phases will be, the field will be real and will achieve perfect focusing. So to summarize, we have shown that in the quantum case, so different configurations of the SLM and different relative locations of the two detectors result with either reduced, same as classical, reduced enhancement or improved enhancement in these different configurations. Now, I remind you that in all of these cases, we actually assumed that the random medium is modeled as a unitary matrix. You can think of a multimode fiber. However, in real life, so things aren't always unitary. You have some light which is reflected, you can have some mode-dependent loss, and in general, in real scattering medium, so not all the light that is inputted to the scattering medium will actually get to the camera at the other side. In this case, so it is common to model the scattering medium as some random Gaussian matrix, where each element of the matrix has a real and imaginary part which have a Gaussian distribution. It turns out that in this case, so this self-consistent optimization problem actually yields quite impressive enhancements. And what actually happens here is that this optimization is able to simultaneously enhance two things. It also couples the light to modes that have less loss, or it brings more of the light to the other side of the scattering medium. And simultaneously, it also focuses the light to a single spot, or localizes the correlations. So with that, I will thank you very much for your attention, and you're welcome to see the paper on arXiv for the full details. And if you have any questions, so I'll be happy to get an email from you. Thank you very much.